Okay, we have a lot of work to do, so we better get right to it. What I want to do is to make a model of a wave on a string. Let me go ahead and show you this video. I made this video. So I live in Louisiana. I don't know if you know that. I live in Louisiana. And these are Mardi Gras beads. You can find these everywhere, but I cut them, and then I'll explain but I give a little tap, and you can see a wave pulse going down the string. And I want to model that in Python for a reason. Okay, so let's just go over an important thing right here. So I have my beaded string right there, and it is attached to another string that goes over this pulley, and then so I can hang a mast on here. In this case, there's 20 grams hanging down the bottom. That gives me a tension in the string. That's kind of important. I can take that whole thing and put it on a scale, 25 grams. That's important. And then I can measure the length. I got 1.2 meters, so that gives a mass of 0.025 kilograms and a length of 1.2. The tension, 20 grams times, convert that to kilograms, multiply by 9.8, 0.196 newtons. That's important. And then finally, the linear mass density, the mass divided by the length. I have both the mass and the length, so I can get that too. So that's kind of important. So let me give you a brief recap of how we can find how you could model the wave on a string. And I have a whole video on this, and it's not super trivial, but I'm going to make it trivial because I don't want to really waste my time on that. Imagine I have a string and I break it into finite pieces, which is what I'm going to do anyway. And I make some assumptions about each mass can only move up and down in this direction. The angles are really small and all these assumptions. Then that mass right there, labeled number 2, has 2 forces on it. There's a tension towards 3 and a tension towards 1. And the net force in the y direction is just the mass of that piece, which I call delta M. And yes, I'm going really fast because I already did this. Okay, and I'll link the video down below with the whole derivation of this. So mass times acceleration, and that's going to be t1y plus t3y. And here's the trick. If I look at the spatial arrangements of the masses and I get this right triangle with delta y, delta x, and the length between them, that's going to be the similar triangle for the tension, right? Because the tension's pointing towards T3. So if I set up a similar triangle between these two, a force triangle and a distance triangle, I get this relationship. And here's a trick, making the length between those two approximately equal to the change in x because it's a small displacements. Then I get T3 as the tension, which is the tension's constant through the whole thing, delta y over delta x. And then if I just choose delta y as y3 minus y2 for tension 3, and then y1 minus y2 because it's going the other way for T1, which is pointing towards T1, then I can get the net force, and I just group my terms together. Again, I'm going super fast. And what happens, and that's the mass times acceleration, but the acceleration is the second partial of y with respect to t, right? That's how we define acceleration. And it's a partial derivative because it only can go in the y direction. And then that mass term right here, this mass term is the linear density times delta x. Now I can just move that delta x over on this other side. I get this expression over delta x squared, and that's, I didn't show this, I'm telling you, that's the same as the partial of y with respect to the second partial of y with respect to x. It is. Now if I put that all together, I get this stuff right here divided by, I divide both sides by mu delta x. I get t over mu over here, and I'm going to call that, and this, I did switch order, I'm going to call that the velocity. So this is the wave equation, and the velocity would be the square root of t over m. That's important. So the wave equation in one slide, boom, did it. But the velocity depends on the tension in the string and the linear mass density, and that's really what I wanted to show. Okay, so that's important. Let's go back to the bead. So here's my bead, a picture of the bead on the wire. What I did was to record the video of this. You already saw the video. And use video analysis. I'm using Tracker Video Analysis. I'll put a link down below. And it wasn't too bad, right? I scaled the whole system using my meter stick. That's why it's there. And then I just marked the location of the maximum point so I could see how that wave pulse moved down. And you can see the the points on here where I marked it in different frames. And if I know the frame rate, which I do, I know the scale, which I do, I can get position versus time for that pulse, and it looks like this. So this is just the before part. There's my pulse moving down the string, and since if I'm plotting position versus time, the slope of that would be the velocity. And I think that's kind of cool. So, but also I could calculate the velocity based on the tension, which I know, and the linear the linear mass density, which I know, and I get 3.07 meters per second. That's what it should be based on the weight hanging over the end and the length of the thing divided by that. I can also get it from here. You can see from the slope that this is 2.85. So they're not the same, but they're pretty close, right? That's pretty close. I was pretty excited to see that. That's a pretty good result for me. So now what I want to do is to model this same thing in Python, because if you can model it in Python and you also get the same velocity, then we're going to be golden here. Let me tell you something. I'm setting up this. I'm going through the rough outline, and then I'm going to do it live. I'm going to program it live. So that may take a little bit longer. I mean, might be some mistakes, but let's just do it. So the key here is to break this into finite elements and to model each piece of the bead. It could be a uniform string too, as connected by springs. So we need to do a really quick review of how springs work. So suppose I have a mass on a spring and it has some vector length of the spring L, and that's from the beginning of the spring to the mass, right? That's my vector length L. It also has some unstretched length. So in this case, it's actually longer than its unstretched length. So if I pull it longer than it should be, there's gonna be a force pulling. Whoa, wait. That way, backwards. I always get my arrows wrong because of this thing. Now I am going to use another thing. I'm going to use this L hat. L hat is a vector in the direction of L. So if you just use your normal Hooke's law and use, stretch and K times stretch, it's not going to be a vector, and I need a vector because these things are going to be in two dimensions. And then finally I get this vector force, Fs, the spring force, and I can write the following expression for that. Negative K is the spring constant. I have to take the difference between the magnitude of that length and the unstretched length, which is not a vector. I have to take that difference. How much did it stretch? And that's that L magnitude minus L0. Then in order to make it back into a vector, I multiply by L hat. So L hat is a unit vector in the direction of L. That was spring force. And I put a box around it. I like to put a box around things I think are important. I think that's important. Okay. So here's my bead string. And again, this should work for any string, even though my beads actually had finite masses. It just worked out nice. So I want to break the string into finite pieces. Here I have a string of length L, and I broke this into 5 pieces. This is an example. We can do as many pieces as we want. So the first thing I can do is calculate the mass of each piece, right? So if I know the total mass, capital M, and I divide by the number of masses, that gives me the mass of each piece. I also need this piece up here, this stretch. This is the distance between these pieces, right? I need to know that. So in this case, you'll notice that I have 1, 2, 3, 4, 5 masses, but 1, 2, 3, 4 springs. So I have one less spring because I start and end with the mass. So this S distance is going to be the total length divided by N minus 1. Now, you could just do N. If you have like N is 1,000, then you're looking at 1,000 or 999, and it's not going to be that big of a difference. But I like to do things the right way. So now the other thing is that if I could say, and I'll actually change this later, the unstretched length is the distance between those springs. And I'm considering these as point masses, so I'm going from the center to center. Okay, and that's going to be my S. The S is going to be my unstretched length for now. And then I could calculate, let's say I have a mass 1 and mass 2, and they both have vector positions. Then the length vector vector L would be just 2 minus 1. Vector addition, I can do that. Now, this is just one thing. I'm going to actually call these springs as an object in Python. And so if I want to look at the I number, spring mass I, it could be anything, then it's going to have two forces on it, one from the next spring, and one from the spring before it. So I'll have to use these indices. I'm going to go over this for you in just a second. You see, we got a lot. I told you we had a lot of work to do, and I wasn't joking. We got a lot of work to do. Okay, so what about how do I handle the tension in my whole string, right? In the real life, I had that string connected to it with a pulley over the end hanging with some weights. But how would I do that in real life? If I take my model, again, I have 5 pieces, and I stretch it, right? Then every single spring stretches, but overall the whole thing stretches, and so that I could have some overall spring constant, right? I have this capital K, which is the spring constant for the whole thing. And, you know, it may not be very stretchy, but it does stretch. Even normal strings stretch. But if I use each one of these with that same spring constant, then each one of them gets stretched, right? And so you have to be careful. You can't, that each individual spring constant is not the same as the overall spring constant. So in fact, I can calculate that by dividing by the number of springs, right? The total stretch of the string is that spring constant. Well, if I had to multiply by the amount each stretches, and if I want those forces to be the same, then the spring constant lowercase k is the spring constant for each of these springs. I'm sorry, I got it backwards. Would be the total number of springs times the total thing, because each one of them stretches, so they need to be stiffer in order to make it stretch the same amount with the same force. Okay, so, and that's important because I don't want to preset that. I want to be able to change the number of pieces in my string model and automatically adjust my K. So that is important. Now, here's how I can set the tension. I can say, okay, this is my stretch, my S. But what if I make the unstretched length a little bit shorter than that distance? Then this is kind of like giving a pre-stretch to the spring. That's important, right? Because I don't have a pulley with a mass hanging over it. I have to give something that would allow me to calculate the tension in the string, and the tension in each spring, the spring force of each one is the same if it's in equilibrium. So all I have to do is calculate the tension right here. It should be the same throughout the whole thing. And I can do that by pre-stretching it. I pre-stretch it by just a decrease in that unstretched length, right? So once I already make these masses, I just make the unstretched length a little bit smaller. By multiplying by 0.9, you could have some other number. And then if you want to just check that tension, it would just be that the stretch, which is 1 minus 0.9, right? Because that's how much it did. And then multiply by this to get the total tension. So you can check, right? If I want a tension of 0.196 newtons, I can make that happen. Okay, so here's our plan. This is what we're going to do. Number one, I need to set up my program. I'm using GlowScript v Python. I'm going to give you the code. I need to set up, I need to calculate my stretch, my unstretched length, my masses, my spring constant, all that stuff. I need to calculate that stuff. And then I need to make all the balls based on the number of pieces that I have and the springs. And then once I do that, what I'm going to do is to take that first ball in the end, and I'm just going to move it up and back down to start the wave. And so I need to come up with a way to do that. And then I'm going to have a loop where I'm going to calculate the force on each ball in that string based on the amount that things are stretched on each side. And then I'm going to use that force on each ball to update the momentum of each ball, use the momentum to update the position, and then move the springs, because the springs are pieces too. And this is your basic Euler method of a numerical calculation. I didn't go over this at all. I've done it a whole bunch of times. I'll include a good link down below. I promise you I will. But the basic idea is to, one, calculate the force on each object, use that force to update the momentum. So in this case, 2 is the momentum at the end of the time interval. I'm breaking it into small time intervals. 1 is the momentum at the beginning, this is for some object. And this is just straight from the momentum principle. So if I know the force and the time interval and the momentum, I can find the new momentum. And then I can do the same thing with position. If I know the momentum at the end, I can use that to find the position at the end of the time interval using the position at the beginning of the time interval. And then update time. And then just do that over and over again. Okay, so we are ready to start. I'm going to switch over here to Python. This is GlowScript vPython. Hope that's big enough for you to see. And I did put some stuff in here, and I'm going to give you the link. I told you that I would. And if I said I would, I will. Let me just show you what I put in here. So I already put in the length of the string, which is the same as my bead. I want to make this the same as what we have. This is my total mass. And this is my spring constant. I just picked a value, honestly. I was playing around with this before in a different version, and we can change this, and we will. I don't know why I put n as 34, but I'm just going to leave it. You could have the same number of masses as beads, but it shouldn't matter. I can have n as 1,000. It's just going to be a lot more calculations. I picked my overall spring constant of the whole thing, which is actually kind of low, but and then this calculates the spring between each one. M is the mass of each piece. It's just the total mass divided by n. This W is actually omega, right? But I didn't want to type omega. This is the angular frequency of the pulse. So it's essentially a wave. I wanted to make a little wave like that, but I'm just going to do a quarter of the period. Well, half of the period. And so I'm just going to go up and down instead of a full oscillation just to make one pulse, just like I did in the video. A is the amplitude of that pulse. Again, I picked something that you could see. This is something you can change. TP is the time. It's half the period. Because I don't want to have this thing keep on moving forever. I just want to make one pulse. Okay, so what do we need to do now? The first thing we need to do, what I want to do is to make 2 points in space. I want to make a left end of the string and a right end of the string. So I know it has to be a length L, and I don't want to put it at the origin because the camera shifts around a little bit and it doesn't look perfectly. So let's just do this. I'm going to say left end, it's just a vector. It's just going to be equal to vector negative L over 2, 0, 0. And then right end is going to be left end plus vector L 0, 0. So then that way it'll be split over the origin. You don't have to do that, right? But doing that makes it so it's centered. That's all I did. And I just want it to be centered. Okay, so the other thing I want to do, I'm going to make a list of balls. I'm going to start at the left end and move to the right end. But I need to know how far I need to move in each step. So let's call this step size. I'm going to call it DS. It's my step size. So it's going to be vector 1, 0. I'm going to be moving in the X direction. 1, 0, 0 times L divided by n minus 1. Because that's the step size, right? It's the same as the length of the spring. Okay, let's go ahead and pick the radius. I'm going to make a bunch of balls. That's what I'm going to do next. So let's pick the radius of each ball, L divided by, I want it to depend on n. So let's say 5 times n. Let's just try that. L divided by 5n. Let's just try that. I don't want to go into lists too much, okay? So I'm going to give a quick list example. And then I'll include a link down below for my list tutorial if you need that and if I don't forget, and I might forget. So let's do this. Balls equals a list. So a list in Python is really just a list of things. And the nice thing in there is you can put 3-dimensional objects in your list. And that's what I'm going to do. But I'm going to start off with an empty list. And then I'm going to say this. For I in range of n, right? And remember we said n is 34. Let's just do this. Print I. I just want to show you how it works. I'm going to print I. And so it just did 0 to 33, right? Because it started at 0. Now let's add that to my list. Let's do this. Balls equals balls plus a list item, just the number I. And you can do append. I don't like doing append, but you do it the way you like. I think this makes more sense. And this for I in range is really nice. It just says I's. It just does a whole bunch of stuff. And then I can print my balls list. And it'll be a simple list right there. And that's kind of nice. I'm using numbers right now, but I'm going to put the other things in there. And then I could do something like print balls 0 is the first one, right? I can go through an index of each one. Print, excuse me, balls 10 would be the 11th one, and so forth. So ball 0, 0, ball 10 was 10. And there you go. Okay, but what I want to do is to make a ball. I want to add a ball in there. So I'm going to say I'm going to add a sphere. And I don't need to give it a name. It's in that list. I can reference it by its list indices. So I'm going to make a sphere. Its position is going to be equal to I'm going to start with the left end plus the vector ds times I 0, 0. All right, so when I start off when the first I is 0, so I'm going to get my first ball is going to be at the left end. My next one's going to be ds over to the right. My next one's going to be 2ds over to the right, 3ds over to the right, and so forth. No, I did that wrong. ds is a vector. So it's just going to be I times ds. That's my position. Now, the sphere, I need to also give it a radius. So let's say radius equals r. What else do I need? Oh, let's give it a mass. Mass equals m. That's kind of dumb. Let's do this m over n. And then let's delete that. I don't like doing that. It would work, but I don't want to do that. What else can I give it? I could give it let's put a whole bunch of parameters in there. Let's do this one too. I'm just gonna put a return here. I can. P equals vector 0, 0, 0. And then this F equals vector 0, 0, 0. So I'm gonna have a balls.f. That's the net force on my ball. Ball.p is the net force, the net momentum. Not the net, it is the momentum. And then I need parentheses to end that and that. Okay, so let's just do this. Print, I want to check it. Balls 4 dot p. Let's just see if that works. Okay, and well, we should see all the balls there too. They should actually display them. Okay, there you go. There's all the balls. You can count them if you want. You can rotate around. I think the size is good. I'm pretty happy with that. So there's my list of balls. Okay. Now, and the way I did it, if you make more balls, the radius is going to get smaller, which you may not want to do. But you do you. And it did print out the momentum of that ball. Okay. So I did set all these properties. So it has zero. Each one has 0 force, 0 momentum. Everything is golden. Okay, what do I need to do next? Let's make our springs. So I'm going to say springs, which you actually don't have to do. You know, especially if you have a whole bunch of balls, you don't have to connect them by springs. But I'm going to use the property of the springs to calculate force. So I actually do want to do this. So it's another empty list. And let's just populate that for I in range n minus 1. Remember, there's one less spring. And so let's just say springs equals springs plus, I'm going to add into it a cylinder. So a cylinder in VPython is an object that has a position, which is one end of the cylinder, and then an axis, which is a vector from one end to the next. So let's do this. Cylinder. So I need the position. POS equals the same thing. Left end plus I times ds. It's the same thing, right? The only thing difference is it's not going to be to the end because I only go n minus 1, so I start at the same place. So my position is going to be on the mass before it, and then my axis, they're all going to be the same length. So axis is just going to be equal to ds, which is a vector. And then I do need to give it a radius. So let's say radius. I had r, let's say r over 2. Yeah, let's just try that. Let's save this. Run it. Okay, so there's my mass is connected by sticks. I think I'm pretty happy with that. Okay. Moving right along. Aren't we having fun? Okay. Now, what do I need to do next? Okay, I need to pick my stretch amount, right? So up here, I'm going to say L0 equals, what am I going to call it? I said, okay, this is from my thing, 0.9 times L divided by n minus 1. Right, so if I had no stretch, it'd be 1 times L divided by n minus 1. But that, I'm not displaying anything. I'm going to use this in my calculations. Okay, I'm looking at my little notes here, because, yes, this one's kind of tough. I could, let's just do it. Oh, I need t equals 0, dt equals 0.0001. Let's do that. I want to really a short time step, because if my time steps, if I have a fast moving wave, I need a really short time step. And, 3 meters per second, that's fast enough that I think I need to do that. Okay, so let's start this. While t is less than how long do one run it? For 1 second. I just picked that. Rate is 10,000, right? Yeah, so rate is a property in GlowScript v Python that tells this, don't do any more than 10,000 loops per second. So it should run in real time. You can change that. You can make it smaller if you want to run in slow motion. You can increase if you want to make it faster and so forth. Okay, now, I actually have 2 special cases, right? If I treat all these middle balls, they're all the same, right? They have the mass before it, the mass after it. But the first mass does not have a mass before it. And the last mass does not have a mass after it. So I need to calculate the force on ball 0 and the last ball separately. Yeah. I don't think, I could just set it equal to 0 because I'm going to move that first ball. I'm trying to decide what I want that end to do, right? Because once I move it, if I could either let it go and let it do whatever it wants, or I could hold it fixed in place. And I'm not sure what the answer is. Let's just leave it alone and not give it a force and not move it and see what happens. I'm not sure. Okay. So I'm going to say, I already have the net force on ball 0 is 0. I already set that. So now I just need to go through all the middle balls. So let's do that. For I in range 1 to n minus 1, right? So now I is going to not start at 0, it's going to start at 1, which if I want to index the balls, I don't want to do ball 0. I don't want to do ball n. I just want to do all the ones in the middle. And that's what this will do. So now I can go through and calculate the force on each ball. So this is going to be complicated, right? Because I need to calculate the force on the ball on the left, from the ball on the left, and the ball on the right. So I'm going to say balls I dot F equals negative K times the magnitude of, I already have the length of the springs, right? I already set those in there. So I just need to springs I minus 1. That's the length, that's the dot axis. That's the length of the spring on the left. That's your left. And I take the magnitude of that. Is that okay? And then minus L0. Right? I'm using that same formula I had before. Now I do need to multiply that by the unit vector, so I'll say times norm of springs I minus 1 dot axis. Okay, so that's that force on the mass due to the mass, the spring on the left. Okay. Now I'm going to add on here the next one. I need to do the spring on the right. It's going to be the same thing, but it's going to be plus, right? Because now I'm looking at the opposite direction. All my springs are pointing in the positive x direction. I keep moving my arrows wrong. So let's just copy this part, and paste it right here. And so what I want to do is just change this to I plus 1. No, to I, right? To I, because the spring to the right is just the same indice as that mass. And this is going to be just I. And since it's going to the right, this is going to be plus K. I think that's right. Okay, so that's that. That's the net force on ball I. Pretty easy, right? Okay, now what about the last force? I don't think I need to do that one. If I don't move it, if I make it fixed, it doesn't matter what the force is. I don't think. Okay, so now all the balls have momentum. All the balls have a net force dot F. So now I can do this. For ball in balls, this is my favorite Python trick. This just goes through all the list items in balls and calls each one ball. Okay, so it starts with the first one, and it calls it ball. And then it does it for the next one, it calls it ball. So I can reference each item like that. So now I can do my Euler calculation. So I can say ball.p equals ball.p plus ball.f times dt. Right, that's my moment. So this is such a great equation right there, because these are, this is the p at the beginning of the time interval, this is the p at the end of the time interval, and this is all the balls. I'm just doing all the balls. Now I need to also update the position. Ball.pos equals ball.pos plus ball.p times dt divided by ball.m. I mean, that's just great. Whew, okay. Now I need to do what? Yeah, I'm not moving that first ball yet. I'm just getting the things to work. Now I need to update the springs, right? Because I moved all the balls, so I need to update the springs. So let's say this. For I in range 1 to n, right? I want to start with the, do I want to start with the first one? No, yeah, I do. I want to do it this way. So I can do it like this. Springs I minus 1, which is the first spring, right? I minus 1 is, you could do this as I. I did it as I minus 1. Dot axis equals balls I dot POS minus balls I minus 1 dot POS. So that means it's just going from this ball to the next ball. That's all I did. That changed the axis. I also need to change the position, right? Because all those balls moved and the spring is attached to the ball. So I will say springs I dot POS equals, no, I minus 1 equals, oops, balls I minus 1 dot POS. Because the ball is moving, I need to reassign that. Okay, so finally I need to do one more thing. T equals T plus dt. So this, I'm going to run it. And remember, there is some stretch in there. I don't think too much will happen. But let's just see. Okay, so it's running for 1 second. I should probably put finished. Let's do this, but let's print out some stuff here. Let's print out the tension in the string just to make sure that it's working. I want it to be 0.196, and I think I picked things so that it did already do that. Let's see, how did I calculate that? So let's calculate this. Oops. TK, I called it. Where did I put that? TK. So I'm going to say TK, which is the tension in the springs. It's just going to be, and I actually wrote this down before. K, it's just the magnitude. K times the magnitude of, I'm going to pick just a random ball to do this, because I want to do it somewhere in the middle. Magnitude of balls 7 dot POS minus ball, I'm doing it manually, balls 8 dot POS. All of that minus L0. That should be my tension. So print tcalc equals tk in newtons. Let's run that. Oh, so you see it's pretty much the same. So that's good. Okay, so next what I want to do, I know this video is going really long, longer than normal. I do have a couple more important things to do. The next thing I want to do is to move that first mass. Okay, so down here, I have that TP, right? that TP. So if the time is less than TP, I need to be oscillating that first ball. So I can do that by saying the following. Okay, right here. I'll put it before. I can put it up here at the top. Let's put it up here at the top. If T is less than TP, then I should be moving that ball. And that means that balls 0, the first one, dot POS equals left end, right? Because I want to start right there. That's my vector position, plus A times cosine omega times T. And then that's the displacement in the y direction. So I need to actually say which way it is. Vector 0, 1, 0. So that's going to be moving up and down this way. And that is the, if it's less than that. Otherwise, I don't even think I have to do an else. Well, let's just do it. Else. Yeah, otherwise I'll leave it where it was, which is fine. Else balls 0.pos equals left end. Okay, I'm kind of nervous about this because I changed some things, but let's just run it. If you don't take a risk, I don't know what you're doing. I mean, that's not bad. That's really not bad. Now, one of the things I want to do, I mean, this is not super realistic. Let me run it again. You can see I do get that pulse moving down there. It bounces back, back and forth and so forth. That's fine. Let's just add a little bit of like a drag force to it to make things not jiggle so much. It makes it look a little bit more realistic. I don't think you have to do that, and I probably shouldn't do that at all. So let's pick a drag parameter up here. I'll put it up here. B equals 0.05. And I'm going to say the momentum, I'm just going to multiply this by the momentum of each ball and add it as a force. So negative B times its momentum, which really should be velocity, but it doesn't really matter. You can just change it to whatever you want, and it should work. So down here, when I calculate the force, so there's my force due to the two things. I'm just going to say minus B times, oops, is this right? Yes. B times balls I dot P. So there'll be a little drag force. Let's check that out. It's still wiggling quite a bit. It doesn't look like it did anything. Let's make this a little bit bigger. 0.1. This is still moving quite a bit. This one's weird looking right, but that pulse looks good. It's not. Why is that moving? Okay, I'm gonna proceed. I'm gonna proceed. I think it's just. I'm gonna proceed. Okay, because I want to make a graph of the pulse width as a function, the pulse as a function of time, because the whole thing is I want to see if I get the same velocity. I have the same mass density, I have the same tension. I already checked that. If I get the same velocity, that's a win right there. So let's do this. I'm going to come up here. I'm going to make a function. Let's call this. Let's put it right. Let's just put it up here at the top. I'm not the best with functions. So def. Let's call this max xy. And give it stuff. So this, what I want to do is pass a list, the balls, and I want to find out which one, I want to get the x position of the ball with the highest y value. See, so that will tell me where my peak is, right? Because I can't just plot the position versus time, because which ball would I plot the position of? I could plot them all, but it's just going to get crazy. So let's just do this. I'm going to say y max equals 0, x max equals 0. And then I'm going to go through all my balls and see which one has a y value greater than that. So for, I'll call it BB in stuff. right? Stuff is a list. I passed it to it. If bb.pos.y is greater than y max, then that's going to be my new y max. So y max equals bb.pos.y, and that's going to be my x max. X max equal not bb.pos.x, right? So that's going to be my x max. It goes through all the ones that finds the one with the highest y value, and it sets that to the x value. And then I just want to, after I do that, I want to return x max. I called it x max. It should be x position. That's fine. Return x max. Okay, now let's go ahead and make a graph. So I'm going to say, let's put it down here. G1 equals graph. Title equals wave string. String wave, I don't know. X title equals, got to spell that right, time in seconds. Y title equals X. So just wave pulse X min meters. Let's give it a width of 600, height of 300, and then that just makes the graph. Then I can plot F1 equals G curve, color equals color.blue. Okay, so that's, I can now plot stuff. Now down here, I'm going to plot in my loop. I'll do it right before the time. Oops. So I'll say F1.plot T, and then I want to plot the position, right? So it's going to be Y, what did I call that? Max XY. Max XY of balls. I think that will work. Did I return the POS dot? Max XY, return X. Okay, I think that should work. Gosh, if this gives me an error, if it doesn't give me an error, I'll be surprised. Let's save it. And run it. Okay. Okay, so this is good, right? Here's my pulse moving down the string, and then weird stuff happens because there's a whole bunch of reflections. So when you get these reflections off the wave, and then the maximum point could be any particular place. But let's just run this until t equals 0.36. So that way we won't have to worry about all that stuff. So I'm just going to change this to 0.36. I'm pretty excited right now. Check that out. I mean, now all I need to do is find the slope of this. And I'm going to show you a little trick for finding the slope in Python. There's a lot of ways to do it, but I'm going to do the simplest way in GlowScript VPython. So if the slope of this would be the velocity of that pulse, and if I get somewhere around 3, that's a win. I don't care how long this video is because it's super long, but that is indeed a win. So let's go up here. I'm going to show you a trick. Graph. There's my graph. I'm going to add up here. Do I do it in the graph or the function? I'll do it up here. Fast equals false. So this will use a different graphing package for the graph. It will actually send it to Plotly, and then we can edit it there. So you'll notice my graph looks different. And if I hover over it, I get these other options here. So you can actually zoom in on it and stuff like that. It's an interactive graph. It's actually a little bit better graph. So if I go here, edit chart in Studio, click that. This is so you notice I'm at Plotly now. And then here's my graph. What I can do over here, now I can edit it. You can change everything you want about it. But the best thing is you can go over here to, oh, you can't see that. Go over here to Analyze, Curve Fitting, Add Fit, and I need to, for some reason it doesn't have a name, that's fine, I click that. And then you say, what kind of fit do you want? I want linear. I do have to give it some test parameters to run, and it fit, very linear, very nice about that. If I click on Advanced, I get a slope of, check that out, 2.957. That is right around 3. This is a win, people. This is a win, okay? I won. I won at Python. I took, let's just take a second. I took a Mardi Gras bead. I have my Mardi Gras bead. See? I took this. I put a tension in it. I gave it a wave. I measured the speed of the wave, and then I modeled it. That was so great. Okay. I know that was really long. Thank you for getting to the end. I will put some links down below for the code and other useful things. But if I miss something, if there's something you need me to add in there, just comment down below and I'm going to add it in there. I want to help you because I love this so much and I had a great time. So that's that.